Hello! In this video we are going to be looking into an example of a sequence of vectors in a vector space for which we would want to establish whether the sequence is linearly independent or not. The vector space that we're going to be working with is the vector space of second-degree polynomials with real coefficients. So let us first clarify exactly what the vectors in this space are before we move forward and discuss a specific sequence for which we will establish linear independence. The notation for this space, the standard notation, is P2. P stands for polynomials, 2 indicates the degree. As a set, we can write it out to be the set of all expressions ax squared plus bx plus c, where this expression is seen as an expression of x. X is just a variable in there, it doesn't have any specific value. You can also think of it as a function of x, but it is not quite a function. A polynomial can be seen as a function, but more correctly it is a formal expression rather than a function. Now, the things that can obtain values are the a, b, and c. And when we talk about real coefficients, what we mean is that these values are real numbers. So the set we are going to be working with in this vector space is going to be the set of all such expressions, in other words, polynomials of second degree. The usual way of writing out a general polynomial, a general element in this set, is p of x or q of x or r of x and so on. So we will often write things down like p of x equals x squared, ax squared plus b of x plus c to indicate one of the elements in this set, or for another element different from the other one we could write q of x, and then we have to put some coefficients there. If we want q to be different from p, we wouldn't use the same coefficients, obviously, so we might use different notation for them. We could say a1 x squared plus b1 x squared plus c1, for instance, or we could define the coefficients and call them instead of a1, b1, and c1, we could go on in the alphabet and call them d x squared, e x plus f, and so on. Concretely, elements are expressions of the form 5 times x squared plus 2, right? This is a polynomial of second order. You might ask, where is the b? Well, the a is 5, the c is 2, but where is the b? Well, in this case, the b term has been dropped because we assume b to be 0. So this is assumed to be this expression where the b is 0. And since multiplying by 0 doesn't change a value, we omit the 0 term. Also, 10 is an element of this set. Here, not just the b, but also the a is 0. So we think of it as a polynomial of second order with 0 times x squared plus 0 times x plus 10, and so on. Obviously, just x squared is still an element of this set, and so forth. Okay. So in this space, addition of polynomials and scalar multiplication are defined the usual way we expect them to be defined. P of x plus q of x is the two polynomials put together. Now, when we put together two polynomials, obviously, so I'm now using the notations I introduced earlier, a and a1. When we put two things together like this is not yet a polynomial of second order, because officially a polynomial of second order needs to be an expression of this shape. And to make into that shape, we're going to group similar terms. So the way we understand addition is that the new polynomial has the coefficients sums of the previous coefficients. So that's how addition of second order polynomials is defined. And scalar multiplication is defined in a similar way. When k is a real number, k times p of x is defined as ka x squared, so ka seen as one coefficient, plus kb x and plus kc. And of course, this way of defining addition and scalar multiplication agrees very well with the laws of addition and multiplication that we have, so that when the polynomials are seen as functions, the addition of polynomials will be usual addition of functions with the usual laws of adding things. And so with the usual laws of adding things, obviously we can rearrange the terms in the way and take things out from the bracket to get this expression we wrote out for the addition, and the same for scalar multiplication. Now, in this vector space, in the vector space of polynomials of second degree up to second degree, we are going to consider the following sequence of vectors. Oops! Oh, there is somebody here. Oh, hello there. Hello! Okay, that was a strange creature there. Okay, so the sequence we're going to look at is the sequence of following vectors. 1, x plus 1, x plus 1 squared, and x squared. Now, each of these terms in the sequence, they are seen as individual vectors in the vector space of polynomials. So we've got 4 of them. Let's introduce an abbreviated notation for them. That will be rather convenient. Let's call this one P1, the other one P2, the third one P3, and the fourth one P4. And to keep the tradition of writing out polynomials, let's put the variable x in brackets here next to the p's. What we want to know is whether this sequence of vectors is linearly independent or not. And to establish that, let's recall what does it mean for a sequence of vectors to be linearly independent in a vector space. There are multiple ways of formalizing this. They're all equivalent to each other, as they should. We're just going to use one of them, at least to start with. So when we have a sequence of 4 vectors, it is said to be linearly independent when the following holds. Every time I can form their linear combination in such a way that the linear combination evaluates to 0, all the coefficients, all the scalars in the linear combination, the c's, c1 up to c4, all of them must equal to 0 as well. So this needs to happen for all the c1, c2, c3, and c4. This symbol here represents the statement for all. You can also think of it as for every. And the brackets go this way. So it is not that this thing should be 0 for every possible c's from c1 to c4. No. What should hold for every possible values for c, which are scalars, so let's indicate that here, is that if the linear combination is 0, then those c's must be 0. And that should happen for all the values of c. In other words, what we're saying is that there shouldn't be a way to have at least one of these c's non-zero, but the linear combination still being 0. That's basically what the condition says. In order to figure out whether this whether this sequence of vectors we are working with right now, the 4 vectors, whether it's linearly independent or not, it might be clever to see how the expression looks like. The expression with the equality to 0, see how that looks like. Because P1, P2, P3, P4 are not just abstract vectors in our example, they are concrete vectors. So this expression can be evaluated concretely. And once we evaluate it concretely, maybe we will have a more insight than we have in general, whether the sequence is linearly independent or not. In other words, we will have a bit more insight as to what does this condition say in the specific example we're working with. So that's what we want to do as a next step, and which is to evaluate this expression in the specific example that we have. So, what will be that thing? C1 times a P1 of x is 1, right? So this is C1 times 1 plus C2 times x plus 1 plus C3 times x plus 1 squared plus C4 times x squared. And now, as per rules for adding and multiplying polynomials by scalars, what I need to do to evaluate this expression is to rearrange the terms according to the usual laws for addition and multiplication of numbers, and then the polynomial we'll get as a result will be the linear combination we wanted to compute. Okay, so let's start looking at the square terms. So there is one square term here with C4, and there will be another one coming out of this x plus 1 squared. So altogether we'll have C4 plus C3 times x squared. Now let's look at the x terms. This term here is going to contribute with 2c3x. And we also have another x term here, which is c2x. So altogether it's going to give us 2c3 plus c2 times x. And finally, the 0th power of x term, which has no contribution from this side, from the blue side. From the green side, the contribution there is c3. And then from the orange part, the contribution is c2. And also we have a c1 from the yellow part. So altogether, that gives c3 plus c2 plus c1. Now that thing, which I'm going to now put in a pink box, this thing is what the expression here evaluates to in the specific example that we're working with. We're now going to use that knowledge to understand what does linear independence in the case of these four vectors, these four specific vectors, state. Here is our green friend watching over us. Thanks for watching. You're welcome. I'm trying to align the slide to the camera, which I'm not succeeding. Okay. No, that doesn't work. Can I help you, maybe? I'm not sure you can help me, you know? Because I don't think you are able to move this thing better than I can. It's a matter of luck, I guess. Doesn't work. Great, I think I succeeded, but I had to pause the video and spend a couple of minutes figuring out how to do it. Coming back to where we were, and where we were was that we have computed the expression in the definition of linear independence to be c4 plus c3 times x squared plus 2c3 plus c2 times x plus c3 plus c2 plus c1. And the definition of linear independence says that whenever this is 0, this should imply that all the c's are also 0. And now we need to figure out if this is so or not. To figure this out, first we need to, well, obviously the thing we want to do is to examine when is that thing 0, right? But before we do that, we want to understand what does it mean for that thing to be 0. So what does this equality actually mean? On the left-hand side of the equality, we have a polynomial of second degree. On the right-hand side of the equality, we also need to have a polynomial of second degree. We need to have a vector here. And what we have there is 0, so that's the 0 vector. And the 0 vector is the 0 polynomial. That's the polynomial where all the coefficients are 0. And this equality needs to be equality of polynomials. Two polynomials are equal if their coefficients match, right? So this equality says then that the coefficients of the left-hand side vector, polynomial, should match with the coefficients of the right-hand side polynomial. Now the coefficients of the right-hand side polynomial are 0 throughout, so c4 plus c3 must be 0, because that's the coefficient of x squared. And 2c3 plus c2 must be 0. And also c3 plus c2 plus c1 must be 0. What we get as a result is a system of equations, where the unknowns are c1, c2, c3, and c4. What we want to see is whether or not this implies that all the c's are 0. So in other words, what linear independence amounts to the specific 4 vectors we are working in this example is for this system of linear equations to have exactly one solution, and that solution being all the c's being 0. So basically we need to solve the system and see what the solutions are there and see if by some chance 0 will be the unique solution of the system. How do we solve a system of linear equations? Well, we have a nice technique for doing that, and let's follow that technique. We can set up a system of, well, we already have a system of linear equations, so what we can do now is to set up a matrix for it. But before we set up the matrix, it might be useful to perhaps rewrite this equation in a slightly different way, which later on will help us get a matrix to be as close to row echelon form as possible. Okay, so I'm going to make some rearrangements. I'm going to first of all order things the way it should be ordered. C1 plus C2 plus C3. So this is 1 times that, 1 times that, 1 times that. And then we have plus 0 times C4. And that should be equal to 0. So that's this last equation, which I now brought to the front as the first equation. The next one, I will now put the second one as the next one, keeping in mind of my row echelon. So here we have 0 times C1 plus 1 times C2 plus 2 times C3 plus 0 times C4. And that's equal to 0. And in the third equation, we have 0 times C1 plus 0 times C2 plus 1 times C3 plus 0 times, no, not 0, sorry, plus 1 times C4. And that's equal to 0. So the matrix we get out of this is the following. 1, 1, 1, 0. And this is an extended matrix. On the other side, we have 0. The second row gives us 0, 1, 2, 0, 0. And the last one gives 0, 0, 1, 1, 0. As we can see, the matrix is already in the row echelon form. So what we can do now is just proceed and write out the solution out of the row echelon of the matrix. I'm going to copy this matrix down so we can use it in the next slide as well. There we go. Let's see if I can have a better success this time. Aligning this thing, I don't. The trick I used was to resize the window that you can't see that I'm working with. Doesn't work either. Okay. Maybe I should just give up on this. But I really wanted that frame to be nicely... Oh, there we go. It worked. Okay. So this is the matrix out of which we can write down the following solution. Okay, so it's not a... The number of equations given is less than the number of unknowns. So it is not the case where the last equation tells us what C4 is, right? In fact, the last equation, which is C3 plus C4 equals 0, right? That's the last equation. That's the one corresponding to the last row. And what we've got here is two variables, and we want to assign values now to them. But we can see that there is some choice here, and namely, we can choose C4 to be anything we like. I could also think of it this way. I could have extended this matrix by adding another row, but the other row, so that then I have a same number of variables as I have equations, and then except that the other row would have just zeros in there. And when this is the case, so now this is more traditional row echelon form of a matrix. When this is the case, the last equation would tell me that C4 can be any real number. Wait, what's going on here? C4 can be any real number? Remember, we want all the C's to be 0. Now this tells us C4 can be any real number. The other C's will be expressed in terms of C4, but C4 can be any real number. So C4 doesn't have to be 0. We don't even have to continue solving the system. We now already, at this point, we know that linear independence fails, because that equation we had in the beginning does not force all the C's to be 0, because C4 can be any real number. So, the sequence of polynomials we started with, let's go back to that thing. Here we are. So this system of polynomials, this sequence of polynomials, where are we? There we are. This sequence of polynomials cannot be linearly independent, because C4 can be any real number. Now, if I want a more explicit confirmation of the linear dependence of a sequence, right? When a sequence is not linearly independent, it's going to be linearly dependent. So if I want an explicit confirmation of linear dependence, I do have to work out the other C's as well. C4 is any real number, then C3 is equal to minus, I mean, I don't have to mathematically, but if I want to emotionally get convinced of myself by having an explicit equation written out with some specific non-zero values of C, making that expression 0, then I would be maybe a bit more happy. So C3 being equal to minus C4, then after this we should compute what C2 is, and C2 will be minus 2C3, right? And remember, we said that C4 can be any real number, so we might as well just pick one value for C4, and let's pick an easy value, not 0, because we want it to be non-zero. So let's pick C4, for instance, to be 1. So let's say we pick C4 to be 1, then C3 will be minus 1, and C2 will be 2. And now, with C2 being 2 and C3 being minus 1, C1, well, in the general case, C1 was supposed to be minus C2 minus C3, that I can see from the first line of the matrix. So now C1 will be minus 2 plus 1, which is minus 1. So, when I choose these values for the C's, let's see what I'm going to get. I'm going to get minus 1 times 1, so that's the first polynomial, plus 2 times the second polynomial, x plus 1, plus minus 1 times the third polynomial, x plus 1 squared, plus 1 times x squared. This is supposed to be equal to 0. And let's see if it is. Minus 1 here will give me with the other one. Maybe I should just like compute the whole thing. It's easier, I guess. That's what we have here. And this minus 1 here, with the minus 1 there and the 2 there, they go away. And the x squared here goes away with this x squared, and the 2x with that 2x. So in the end, it does end up being 0. It ends up being 0 without all the coefficients being 0. So we found non-zero coefficients. In fact, we found coefficients where none of them are 0, right? Minus 1, 2, minus 1, 1. As soon as at least one of them is non-zero, already it's not linearly independent. So it doesn't matter whether it's more than 1 or not. As soon as at least one is non-zero, already that would have made the sequence linearly independent. And here we have it. This sequence of vectors in the vector space of second degree polynomials turns out to be linearly dependent. Could we have detected that this is linearly dependent perhaps in a bit quicker way? Well, sometimes it is possible to take shortcuts. You see, one of the equivalent formulations for linear independence is that none of the vectors in the sequence is a combination of the others. And by combination, I mean linear combination. On the other hand, if one of the vectors in the sequence is a linear combination of the other vectors, then that would make the sequence linearly dependent. So we could have thought the following way, along the following line. In this sequence, would we be able to get one of these vectors as a linear combination of the others? And then perhaps it is not so difficult to notice that the answer to that question is yes. You see, maybe it would help if we first expanded x plus 1 squared. So this is x squared plus 2x plus 1. And we can see now that we could kind of get the x out by combining x plus 1 and 1. So we could take minus 1 plus, in other words, minus 1 times 1 plus x plus 1. So in other words, plus 1 times x plus 1. This would allow me to express x as a linear combination of the first two. And then I get 2x plus the last one, x squared, so in 1 times x squared, plus 1 times 1. And that is equal to x plus 1 squared. So what's going on here? Calling these P1, P2, P3, and P4, what I notice is that we could express x plus 1 squared as 2 times x. I'll come back to that in a moment. Plus 1 times P4 plus 1 times P1. So P4 can be expressed as a linear combination of x, P4, and P1. But x itself can be expressed as a linear combination of two vectors in the sequence, and namely, it can be expressed as minus 1 times 1, which is P1, plus 1 times x plus 1, which is P2. So I'm just referring to this equality here. So you see, x is a linear combination of P1 and P2, and P4 is a linear combination of x, P4, and P1. Now, if I take this expression and substitute it in here, and then open up the brackets, I would get, as an overall result, I would get an expression of P4 as a linear combination of P1, P2, not P4, sorry, this was P3. I would get P3 as a linear combination of P1, P2, and P4. So one of these vectors is a linear combination of the others in the sequence. And that guarantees that the sequence must be linearly dependent, according to one of the theorems from linear independence / dependence of sequences of vectors in a vector space. And this logic that we did at the end here is something we could have done completely in our mind without writing things down. So it is a bit shorter way, and sometimes it helps a lot, especially to avoid us solving, doing lots of calculations like solving systems of linear equations. Thanks for watching the video.